Our next speaker is Dr. Munan Gong. Before she moved to Germany, she obtained her PhD in astrophysics at Princeton University in the US. Now she works as a postdoc at the Max Planck Institute for Extraterrestrial Physics and focuses on the theory and the simulation of stars and planet formation. Today, she will take us on a tour through the interstellar medium.
So thank you for the introduction. And to start, first, I would like to invite you to take a breath and look at your surroundings. What do you see and feel? The light on your skin, the air you breathe, and the floor beneath you. And of course, the existence of yourself. Where does everything on our planet Earth come from? So in the next few minutes, I would like to ask you to join me on a journey through the interstellar medium, where everything started. So now, please close your eyes and join me on board this imaginary spaceship. You are floating in the empty space of our galaxy. It's dark and cold. The closest stars are light years away. The only things you can see are the faint lights from far, far away stars, like little candles in the complete darkness. You cannot even hear a sound. It seems to be completely empty, even emptier than the best vacuum created on Earth. But wait, you find something. You find some hydrogen atoms around you, 1, 2, 3, 4, and many more. You are surrounded by this very thin air made of hydrogen atoms. The air is a billion times thinner than the air you breathe on Earth. Astronomers call this material the interstellar medium, or literally, the matter between the stars. So you keep looking. What else do you find? For every 10 hydrogen atoms, you find 1 helium atom. They're both created at the very beginning of the universe in the Big Bang. For every 10,000 hydrogen atoms, you find 1 carbon and 1 oxygen atom. They are made in the very center of massive stars through the nuclear fusion of hydrogen and helium. When these giant stars exploded, they create a wealth of different elements that was sent back to the interstellar medium that surrounds you. The more you look, the more you discover. Traces of other heavy elements, sulfur, silicon, iron, and little dust grains. These dust grains are very, very small, less than a micron in size, 100th of the size of the diameter of your hair, floating in the interstellar medium like a fog. The atoms move around, collide with each other, and trigger chemical reactions that form molecules in more and more complex forms. Molecular hydrogen, water, organic compounds. The movement of the atoms and molecules seems random, but they slowly come close to each other with the force of gravity that attracts one atom to another. The effect of gravity is slow, yet unstoppable. After millions of years, a very small part of interstellar medium starts to become denser and denser and denser until one critical moment, the collapse of the interstellar medium into a very hot ball of gas, the birth of a star, our sun. Surrounding the newborn sun, the interstellar medium is still there, but denser from the gravitational collapse and hotter from the light emitted by the sun. The dust particles in the interstellar medium collide with each other and grow bigger and bigger like snowballs, until finally our planet Earth is born with other planets in the solar system. So now please open your eyes and look at your surroundings again, and yourself. And everything on this planet Earth comes from the interstellar medium, the very thin dust and gas in between the stars in the almost completely empty space in our galaxy. So at the end of this journey, you might ask me, how do we actually study the interstellar medium? So as astronomers, we're equipped with two very powerful tools, our telescopes and our computers. The dust, atoms, and molecules in the interstellar medium emit light, and this light can be collected by our telescopes. For example, here is a model of the telescope with the nickname ALMA. Or more accurately, is only a very small part of the telescope ALMA. The whole operation of ALMA includes 66 of these telescopes, and they all work together to collect light from the interstellar medium. But me, as a researcher, I'm a theorist. I don't actually use these telescopes directly. I use supercomputers to model the interstellar medium. The supercomputers are thousands of times more powerful than your own personal laptop. So how does this work? Although interstellar medium is very, very far away, it is governed by the same physical laws that we're very familiar with on Earth. Just like we can model the air circulation on Earth and make weather forecasts with computers, we can model the movement of gas and dust in the interstellar medium using our computers and understand how star and planet form. So what do I do personally on a typical day? I try to solve small pieces of puzzle in the big question of star and planet formation. So for example, in one of my projects, I'm working on a new software that I developed to model the formation of carbon monoxide molecule in interstellar medium. Carbon monoxide is a molecule made up of one carbon and one oxygen atom together. So in the old days, before the invention of electricity, many people would burn coal or wood in their homes to heat up their homes in the winter. And this can create carbon monoxide, which is very dangerous. It's because they're poisonous to people. Although we don't like carbon monoxide in their homes, it is actually very useful in the interstellar medium. They are one of the most common molecules in the interstellar medium. And by collecting the light emitted by the carbon monoxide molecule, we can understand how much cold gas are there in our galaxy and how much of these gas are available for star and planet formation. So my software will model the formation of the carbon monoxide molecule, as well as how they emit light. And my work will help us to understand how stars and planets can form efficiently and how fast can they form in our galaxy. As another example, in another project I worked on recently, I developed a new theoretical model to model how dust grains can collide with each other and how fast they can grow into bigger and bigger dust grains and asteroids and finally planets like our own Earth. So working with my colleagues who use these telescopes to collect data, we can test my theories and models together to see whether my theories and models are correct. So all these very small pieces of puzzles, they come together and eventually points to the big question that all astronomers wonder: where do we come from? And finally, I would like to end with a quote from one of my favorite books, Sophie's World by Jostein Gaarde. Yes, we too are stardust. Thank you.
Wow, this was super cool, Munan.
Thank
Thank you so much for this inspiring talk.
Thank you.
Let's move right away to our very first question from the audience.
Yes.
After the formation of a star or planet, does the interstellar medium change composition such that another star or planet cannot form nearby for a certain period of time or within a certain distance?
So it's two questions, very excellent questions. So I hear two questions. One is whether they change composition, and two is whether stars and planets can form close to each other. I will start with the first question. So yes, they do change composition. So for example, when they collapse, it becomes denser. And this makes atoms and molecules to collide with each other at a higher frequency. And this will help to form molecules in more complex forms. For example, complex organic molecules that we can even find in comets. And the other question is whether stars and planets can form close to each other. So it's true that interstellar medium have different density and different temperature because the collapse of interstellar medium. And in different conditions, stars and planets sometimes can form close to each other and sometimes cannot. For example, our sun is not particularly close to any single star. The closest star is about 4 light years away. However, there are stars that form in our galaxy that's similar to our sun, but they have a sister or brother. They form together and they can be very close to each other. And that's because they form in a different condition. And that's also one of the questions we're trying to understand what makes them form in these different conditions. And planets as well. For example, Earth, we have 8 planets in our own solar system. However, there are other planetary systems that we observe have fewer planets or even more planets. So we would like to ask the question, what determines this diversity? Why do stars and planets form in these different ways? And it's one of the most important questions we're trying to study right now. So I can't give you a complete answer, but we know that they form in different conditions. They form in different parts of the galaxy. They have different densities and temperatures, and that makes them to look very differently across one system to another.
Okay, thanks for this.
Thank you.
The next question comes from Mart on YouTube. What was the very first element in this vacuum in the very, very beginning? And where does it come from?
So the first elements are hydrogen, helium, and lithium. So these are very light elements. And they're created at the beginning of the Big Bang already, so as far as we understand. And all the other heavy elements, most of the other heavy elements, heavier than them, like carbon and oxygen, they're made in the center of the star. So the center of the star is very, very hot, like our nuclear fusion, our power plant that we're trying to make. And this very, very hot temperature and very, very high pressure makes the atoms and molecules collide with each other really, really quickly, and they can make new elements like carbon and oxygen. So it's really, really hard to do on Earth. But at the center of the stars, a lot of the elements are made. The other processes that make the elements, for example, the supernova explosion. During the explosion, make different elements. Neutron stars, different types of star, make different elements. But they're somewhat all related to the formation of the stars. So except for these very light elements like hydrogen, helium, and lithium, most of the other elements are created in the star formation process. And they're given out back into the interstellar medium when the stars exploded, or given out gas in the later times of their lives. And these elements can be incorporated back in the interstellar medium, form the next generation of stars, like our sun. So we think our sun is actually probably the 3rd generation already, and they already contain a lot of the heavy elements.
Oh, wow. This sounds interesting.
Thank you.
The next question is, do we have the means in the laboratory to create a star on a dish?
Interesting question. I think the closest thing that we are trying to do now is nuclear fusion. It's not really the same process. We're using different types of elements. I'm not very familiar with nuclear fusion, but the idea is that you put, light elements together and make heavy elements, So I think that's the closest we can get. As far as I understand, my friends who does nuclear fusion, maybe I have to ask them more. Now we can do it, make new elements from nuclear fusion. But in order for this to be beyond the interest of trying to make new elements through fusion, but we also want to make new energy. Like star makes energy, we want to make nuclear fusion power plants to actually power our planets, power our electricity. And that's still some steps away. So maybe in the next years or tens of years, we'll see that happen. That'll be really exciting, yeah.
Okay. The next question comes from Gary Faya on YouTube.
Yeah.
Oh, no, sorry. I was confused. From Becky on Facebook. How can we simulate an interstellar medium?
So to explain, the interstellar medium is made of gas and dust, like our own air. is made of gas and there's some dust particles, hopefully not too many. And they're governed by equations that govern the movement of them. So they're called fluid dynamic equations, and we solve them on the computers. So, for example, if we know that the initial conditions, like the air on Earth, some places hotter, some places colder, we can model how the wind blows. We can model what weather is going to be tomorrow. So if we know some condition in interstellar medium, to start with, for example, we see the interstellar medium from our telescopes, we can put in these conditions and solve these equations using our computers. And that would tell us where these conditions will go. And next, whether these parts of the interstellar medium will collapse and form stars and planets, and what does it look like? What kind of stars and planets will form? So these are from solving these hydrodynamic equations, or if you want to add other things like the light emitted by the stars, also governed by some equations of radiation. So that you can solve with your computers. Yeah.
This sounds complex. So Sakura asked on Facebook, what happened before the Big Bang?
I don't know. I would love to know. I don't know if anybody can know. Yeah, we cannot observe it. So I think it's more of a philosophical question. If we cannot observe it with instruments and I don't know. There are many theories. But it's a good question.
Okay, so unfortunately already the last question for today. What motivated you to become a theoretical astrophysicist? Were there other fields within physics which you considered going into?
So I loved astronomy when I was a kid. I grew up in a small city where you can see stars. I didn't really think about doing theory or observation. I kind of stumbled upon this when I was applying for my PhD, and I worked with my advisor. She's an amazing advisor, and she worked in the field of star and planet formation, and I really loved it. So it's more of exploration in a specific field, but I loved astronomy already when I was a kid. It's more of a naive love, but I still love it.
Yeah.
In other field of physics, I haven't really thought about it too much. Sometimes I think about it. Perhaps I want to do something related to environmental engineering or something if I'm not doing astronomy, but that's, I'm doing astronomy now, I'm happy. So, yeah.
Okay, yeah, cool. I just wanted to let you know that your audience said, listening to you is very meditative and you should consider starting a podcast because the
thank
perfect
you.
voice for this.
Maybe I'll think about my side career.
So thank you once again, Munan,
Thank you.
for
Thank
your
you very
inspiring
much.
talk.